glad I looked because it did stop recording. Okay. All right. So the idea, an inclined plane is just like a fancy way of saying a ramp. Um, but a couple of important things. So first of all, the angle of the ramp is the same as the angle of the weight triangle, right? And I went through and showed you that proof. But remember, that's only really going to be accurate if you draw the perpendicular force first. Okay, don't draw this force first because that angle uh, is not the angle that's the ramp angle. Hold on, guys, 1 second. What's up? Okay, sorry, I still don't know what he wanted to do. Okay, so we are going to look at mostly the parallel direction. And I see a lot of people when I ask you to, give me the perpendicular or the parallel components, it seems like arbitrary. You just like, it's sine and cosine, but you don't seem to be able to match up what is the parallel and what is the, which one's not parallel. So in this particular, let me see, here we go. So in this, what's weird though? Here we go, I'll do it this way. You know what? I swear to God, my brain is like so broken. I have to think about how do I point at this thing? Well, I was using my mouse, but I realized you guys can't see my mouse. So let me use the actual triangle. This side is opposite the angle. So that's the sine, right? I mean, that's the thing you guys need to make the connection. Sine is the opposite side, and the cosine is the adjacent side. So you're going to have that little angle marker somewhere in the triangle that has the angle that you're dealing with, and one of the sides will be adjacent. That's going to use the cosine, and the other one is going to be opposite. It's going to use the sine. And then the vector itself, remember, this one I drew it in red, and the reason I drew this in red was because I did not want to draw all the forces. So you either have the weight arrow or you have the two components, but you don't have all three of them. I'm replacing the weight with these two arrows because they get me to the same place. The math will work out the same for these two as it would for using this arrow, but a lot easier to deal with these two. So, be a little bit careful about that because I do see people putting mg and mg cosine theta will be in the equation, but that would never, ever, ever be the case. It's either mg cosine theta goes in or mg sine. And then the mg we won't be plugging in at all. So I just wanted to go through to the extent to show you what we ended up with. So first of all, we found an interesting relationship with the coefficient of friction, right? But more importantly, we came up with this relationship that if the frictional force was zero, if there was no frictional force, then essentially the only force that is being applied parallel to the surface is the frictional force. So, sorry, not the frictional force. The, what am I trying to say? The gravitational component that points down the inclined plane. So if there is no friction, look. Here's the two parallel arrows. The frictional arrow, which is going up the slope, opposing the motion, and the weight arrow, and this is really important for you to recognize, this is why the guy is going to move. Whether there's friction or not friction, this is why he's going to move. There is a little component of the weight which points down the slope, and that's the one that's going to make the thing move. And so we have two forces, but I'm saying let's take this one away. Oh, well then there's only one force, mg sine theta. There's only one force, it points in the downward direction, and that force is going to tell me what the acceleration of the object will be. It's not going to be 9.8. It's going to be 9.8 times the sine of the angle. 9.8 times the sine of the angle. Okay, so I'm going to use this relationship. So I'm not going to go back and redo all this stuff because this should be already in your notes, right? So what I want to do is jump ahead and solve the problem using the force method, and then we're going to solve the problem using the energy method. And you tell me which one is easier. I think you will have a good appreciation about why we want to learn about energy. It's definitely much easier to work with. All right, I'm going to go to a fresh page. Yeah. Oh, interesting. Oh, I see. Okay. There we go. Now I see it. All right, so the inclined plane. Let's do forces first. All right, this is all I want to know. Okay, I want to know when this thing gets to the end of the ramp, how fast will it be going? That's all I want to know. When it gets to the end of the ramp, how fast will it be moving? Right? We should be able to work this out by using the forces. So I'm going to look at this situation. We're going to put a little box at the top of the ramp. The ramp will be frictionless. Okay, frictionless ramp. Maybe it's on ice, maybe it's on oil, I don't know. But it's going to go down this inclined plane without any friction whatsoever. I'm giving you some numbers in here. Sorry, I should have left a little more room for that. So on this ramp, we are looking at a ramp which is twice as long as it is tall. Okay, and hopefully you guys kind of recognize this. This is a 30-degree angle. This is a 30, 60, 90 triangle. So on a 30, 60, 90 triangle, the shortest side is half the length of the longest side, and you don't really need to know this, but this is really easy to recreate this. Imagine each of the sides of this triangle is 10. Well, what's going to happen when I cut this angle in half? Well, that's going to be 5. And that's my 30, 60, 90 triangle right there. Okay, so in the 30, 60, 90, the long side is 10, the short side is 5. Very important. Now, from a force standpoint, who the hell cares that this is 5 meters? It's irrelevant. This thing's going to be going this way. That's all that matters. It's going to be sliding down the inclined plane. And we found that A was equal to G sine theta. Okay, now remember, I'm jumping into the middle of the problem. Okay, I'm not showing you all the details because there's an equation that you would have to show this. If all you did is you said A equals G sine theta, you would only get partial credit because you're not showing where does this information come from. But in this case, we can certainly work out what is the value of it. Let's use 10 times the sine of 30 to give us an acceleration of 5 meters per second squared. Okay, so just to realize, the work that I'm showing you is the end of the work, right? What I'm not showing you is the equation for the forces acting on this, and then when we remove the frictional force, then it reduces down to the acceleration is equal to G sine theta. I'm skipping over about 2 or 3 steps that you would have to show in order to solve this problem. So I'm kind of jumping past the part that we've already done to continue on to now figure out the velocity of this thing. So in this case, I now have the acceleration is equal to 5 meters per second squared. I know the distance I need to travel is 10 meters, and I know that my initial velocity is 0, and so what I want is the final velocity. Well, hopefully this is getting more familiar to you guys so that you can see that this is the equation. And I hope it's not surprising that equation comes up so often in the energy chapter, because this is the foundation of the work energy theorem. All you need to do is to multiply by m. You multiply all these guys by m, and you can turn all of these into kinetic energies, and this guy over here will turn into work. So in this case, there's no algebra to do, so let's just go ahead and plug the numbers in. So we're going to do second function square root 2 times 10 times 5. And that gives me a speed at the end of 10 meters per second. Any questions so far? And we're just going to pause here for a moment. We essentially have used forces to figure out what will be the speed of this thing if there's no friction. if there's no friction, what will be the speed of this box when it arrives at the bottom of the ramp? It'll be traveling at 10 meters per second when it arrives at the bottom of the ramp. Okay, so this is about half of the solution of the problem. The other half to the solution was back here. When we were doing these equations. Now the difference would be there would be no frictional force, right? If I take away the frictional force, then ma is equal to mg sine theta, which is exactly what we started with here, and then we ended up with this, right? So just bear in mind that this solution is picking up where this thing ended up, and then here is the final answer. We'll end up with a speed of 10 meters per second. Remember these. V squared was equal to 2 times 10 times 5. Those were the numbers that we came up with. All right, let's take a look at energy. What would energy say? Let's do it right here. All right, well, energy would say, and this is the reason why we're going over this problem, energy would say it doesn't matter how you get to the bottom. It's irrelevant. All that matters is what was your height, which in this case is not 10. The height is 5, right? So the height is 5, and then all we need to know is the value of gravity. And with that piece of information, we can do it because we know that the potential energy at the top is going to turn into kinetic energy at the bottom, right? So at the top, it's all potential, but there's no kinetic. Then it's going to pick up speed as it slides to the bottom. When it gets to the bottom, it'll be at the 0 level for height. So therefore, there's no more potential energy, but now we have kinetic energy. Okay, now the only reason why why we'll be able to solve this problem is because there is no friction. Okay, if you bring friction in, then the problem gets a little bit more complicated, but you can still do the energy approach, and I assure you, the energy approach is easier than the force approach. I mean, if you guys didn't get that from the force chapter, you must have missed something. The forces are quite difficult to work with. It's a lot to think about. But the energy approach is much easier because you don't have to, it doesn't matter how it gets there. It doesn't matter whether this box falls backwards off the ramp and falls straight down this way, or whether it slides down the ramp. It will have the same speed either way. It will have the same speed whether it falls off the back or rolls to the bottom. Now, there will be some differences, obviously. It will get there quicker. It will not take as long to get to this position if it falls off the back than if it goes this way. But just purely in terms of the velocity. Which one of those is going to produce more velocity, sliding down the ramp or falling off the back? Doesn't make a difference. Does not make a difference because energy does not care how you got there. It doesn't matter on the roller coaster if you went up and down, up and down, up and down, but then if you ended at the bottom, it just matters where you started and where you ended. As long as no friction is acting, that's going to determine your velocity. So, in the energy approach, what we would say is the following. EP is equal to EK, and therefore mgh equals 1/2 mv squared. We do not need the mass. You know, in my honors in my regular class, I always give the mass because I could see that some students were struggling, and with the mass, you can do it in 2 steps, right? I could calculate the potential and then set that potential equal to the kinetic and then solve for V. So, but for you guys, you aren't in the regular honors class, you're in the IB class. So you may find that in a problem like this, they do not give you the mass, and if you notice, I didn't need it for the first part either. Notice I was able to get the acceleration without the mass, and I was able to get the velocity without using the mass at all. So this problem does not require the mass, but it's probably going to be given to you most of the time. The majority of the time you will be given the ability to have the mass if you want to use it. Okay, so what I end up with here is 1/2 v squared equals gh. So v squared is equal to 2gh. Looking familiar? Looking familiar? Correct me if I'm wrong. Those are the exact same numbers I had up here. I ended up with v squared was equal to 2 times 10 times 5. I just got the exact same thing. However, I solved the entire problem by showing you literally every conceivable step that I could show you. I mean, I literally showed every single step, and it still did not take as long as the force, because remember, this is only the second half of the problem. You won't even get to this part of the problem unless you can set up that equation. You could get partial credit by starting at this point, but realize on the IB exam, you're not going to have a notebook. So that means you'll have to memorize this equation. That doesn't feel like a good way to do it. Better to understand it by solving the force equation. That ma is equal to mg sine theta. The component of the weight pointed down the inclined plane, that's what makes it move. Because none of the other forces point in the right direction. They're either perpendicular or into the surface perpendicular, or they point up the slope. The only one that makes it move is the component of the weight that is parallel to that surface. So the energy approach, if you don't have friction, super easy approach to use. So in other words, what I'm saying is that imagine we had a roller coaster that went up like this, and that the roller coaster had a very steep hill like this, or one that went like this, or one that went like this. What I'm telling you is it will not make any difference which of those paths you take. You will have the same speed at the bottom. Now, from your standpoint, what will be different? Well, this one will have much more acceleration, but the acceleration won't last for very long because you'll get to the bottom very quickly. The medium one will have a little bit less acceleration, so it's not picking up speed as long, but it has more distance and time to collect that speed so that by the time it gets down here, it will still have the same speed. In fact, we can make this thing very shallow, very gentle. Maybe it'll take you a week to get up to that speed as you slowly, slowly, slowly come down this very slight ramp. But you will have the same speed at the end. Again, assuming that we're ignoring friction, we're ignoring drag, we're looking at a situation where no other forces are influencing this thing at all, then it does not make a difference which path you take. You will have the same speed at the bottom. And that's not necessarily obvious. Now, if friction does play a role, then it does matter. Like you will definitely not have as much speed on this one because this one's going to give that friction such a long time to act, and that's going to steal away a lot of your energy, and so therefore you won't be at the same speed down here. But as long as friction is not there, the path is irrelevant, and the way you would say it is it's independent of the path. So the speed at the bottom of each of these three hills would be the 10 meters per second if the height of this hill is 5 meters. Any questions? Anything you want me to look at again or just repeat? Seems like we're missing a lot of people. Oh, people are going to spring break early, right? Is that what it is? I noticed all my classes are a little bit less than normal. Like missing about 2 people in every class. All right, I don't hear anything, so let me stop the recording. I'll post that again